All right, so for what we have discussed is about how to draw the Lewis structures. We have discussed several rules when it comes to draw Lewis structures. So please remember those rules whenever you are drawing a Lewis structure. Make sure that you're following the steps. Okay. After the topic of Lewis structure, our next topic is bond energy. What is bond energy? When we talk about covalent bonds, the higher the bond, I mean, you know already that when it comes to covalent bond, it can be either a single, double, or triple bond. And bond energy, the order of the bond increases from single, double to triple. The bond energy is going to say more and more energy than this triple bond. Correlates with the molecule with high bond order having short bond lengths. That's why more attraction. You need more energy to break these bonds per mole of the bond. So bond energy increases with increasing electronegativity difference. Okay, that's what we know. Higher the difference between the two atoms for the electronegativity is, more the bond energy is going to be. See, O2F is 190 kilojoule, and if you go by O2Cl, it's going to be 220 kilojoules per mole. So using bond energies to calculate enthalpies. Enthalpies is what we are talking about, the amount of energy to form covalently bound molecules. Okay, requires bond dissociation energy. So actually, the bond dissociation energy is equals to the bond energy. How do we know how much energy is in the bond? We're going to break the bond and we're going to figure that out. Whatever the energy is released out of the breaking of the bond is going to be equal to the bond energy. So bond energy is defined as the energy required to break 1 mole of covalent bond. So now we're going to go by this reaction. If we look at this reaction here, what's going on? So this is actually, see, if you look at the reaction, then this is your, sorry. So this is your CH3. Okay, so we're talking about CH3 first. We're going to go by just reducing the size a little bit. So that's your CH3 here in the compound. What is given to you? The formula is given, molecular structure is given to you. So you can actually look at how many bonds are there. So when any reaction happens, what is this diagram showing us is the estimation of enthalpy change for a reaction from bond energy. So we can calculate that. So let's see what we are going to do. This is Cl2 here. Okay, diatomic chlorine. This is the reaction, and after the reaction is done, what we get CH3Cl. Okay, sorry, this was not CH3. I'm very sorry. This is CH4. Okay, this is CH4. Methane. Methane is reacting with chlorine, so that's going to be CH3Cl plus, we're going to get this HCl. Okay, so HCl and HCl, this is what the reaction is showing in the molecular structure form here and here. So if that is true, so what we are looking for, it's important when we are given the chemical equation or a reaction equation like this, we need to open it into the Lewis structure first. So we can look at that what bonds are there, because we are talking about bond energy. Remember that when we talk about the bond energy, we need to look at the bonds as well. So guys, when this is undergoing the reaction, means all the bonds are going to break and then the rearrangement will happen. Okay, so rearrangement is going to happen. That's why we're going to say these 4 bonds, there are 4 bonds, CH, 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 they are going to break. Then the Cl bond is also going to break. Okay, then what new bonds are formed? 3 CH bonds are formed, and C to Cl, one C to Cl bond is formed, and then H to Cl bond is also formed. So we need to know that, right? So if we know that what bonds are breaking here and what bonds are going to be formed here, um, we can look at how to calculate the enthalpies of the overall reaction, the energy change of the overall reaction. So if you see, this is your um, y-axis showing the enthalpy. Enthalpy is the heat of the reaction. Okay, whatever the heat is going to be coming out of the reaction. So we're going to see. So the reactants were a little higher on energy level compared to. So that means high in energy means more reactive, right? So they're going to go into the reaction. And once the reaction happens, which is actually the rearrangement, bonds are broken, new bonds are formed. And then when we go to the product and we check out the stored energy of the product, we will find what we find is that what we're going to find, or what we have found is that products are low on energy compared to the reactants here, right? So it means some extra energy has been released, and that is what we call the enthalpy of reaction or the heat of reaction. From here, it's going to go high onto the energy, so it can actually go for the rearrangement. That's an energy plot for the reaction to happen. Okay, so what we are saying that breaking C2H bond and C2Cl bonds. This is where it is breaking. Number two, making C2Cl bond and HCl bonds here. So if we are going by that, if you go, if you look at this chart has already been, the scientists have calculated the average bond energies in kilojoules per mole. So we can use these to calculate the overall heat of the reaction, which is delta H of reaction. So as to move forward, this is what is the equation to do that. Okay, delta H of reaction that we are talking about here, if the bond energies are given to us, we can do that. So delta H of reaction is equals to the change in energy of the bonds broken minus change in energy bond formed. So delta H of reaction is equal to bond association energy here, right, to reactants minus bond dissociation energy for the products. And dissociation energies are already provided to you. You have to count for the numbers and the types of bonds. Okay, so how many bonds are broken, how many bonds are going to be formed. This is what you must pay attention to. Now, if you look at this example, which is example 2, you can calculate the heat of combustion for methane. So this is methane. Combustion means in the presence of oxygen, and then you are going to produce carbon dioxide and water. You already know all this part, right? So first step in doing that, what we are doing, we are calculating the heat of reaction, which is the heat of combustion. Okay, so the first thing that says when you are doing this, the first thing is to draw the Lewis structure for all the reactants and all the products. This is super important. You must know, okay, because we need to know what type of bonds are there and how many of the bonds are there, right? So if I draw the Lewis structure for CH4, that's going to look like this: CH4. It means how many C2H bonds are there? 4 C2H bonds are there. If I look at oxygen, I already know the structure of the oxygen. The Lewis structure of oxygen is going to look like 2 times what I have here. What is the Lewis structure here? The Lewis structure of oxygen is going to be like this, double bonded. Okay, you know how to draw Lewis structures now. It means I have, in total, I have 2 double bonds, because do not forget this 2 here. Okay, then what is my formula? I have to subtract the bond dissociation energy of the reactants, bond broken of the reactant, minus bonds formed. So carbon dioxide. If I draw the formula for carbon dioxide, that's gonna be so if I'm going it this way, so the bonds form in the product side, right? So carbon dioxide, the Lewis structure for carbon dioxide is gonna look like this: O, O. I have 2 here, you have 2 here, you have 2 here, 2 here. Okay, so that's my carbon dioxide. It's just one molecule, so I'm good. So then I have 2H2O. So I'm going to say what 2H2O means 2. I already know the formula of H2O. That's going to be O, right? That's going to be H, and there's going to be another H. You know that this is the structure. So how many bonds I have? I have 4 CH bonds here. 4 C2H bonds. I have to figure that out, right? Then plus I have 2 O2O bond, right? 2 O2O bond, 2 bonds. Then I have just one molecule means 2 double bonds. C2O double bond. How many? 2. Then I have 4 O2H bonds. 2 molecules means 4. So it's exactly like this molecule is here. That 2 tells you, okay? So then you're gonna have plus 4, 4 what? 4, oh my God. Okay, so just clean it a little bit, and then I'm gonna say, okay, so that's gonna be 4, how many OHs? 4 OH bonds are there. This is what we have to figure out first. So now these bond energies, we're gonna get it from the table. Okay, the numbers are here in the table. Let's say, what is the number for C to H bond? So that's gonna be 413. So I'm gonna say, if I'm solving it, I'm gonna say, okay, 4 times 413. Okay, minus, no, not minus, plus. Okay, plus what? What do I have? What bonds I have? O to O. Okay, two of O to O's I have. So I'm gonna see where I have O double bonded O. O double bonded O here. That 498. Okay, and two of these means 2 times 498. Then minus 2 times, and this is carbon dioxide, which is a special case. If you go into the chart, you see C double bond O is different in C carbon dioxide, which is 799. Okay, so I'm going to take 799 for two of these. Then plus 4 times what is this for OH. Okay, so I'm going to go into the OH. Where is OH on the table? So OH is 467. Okay, 467. So it's a quick maths now, right? Quick math. Just keep multiplying that and keep getting that. So if I do that in my calculator, then it's going to be, so that's going to be in 2918. Okay. So these numbers were given to me in kilojoules per mole. So that's going to be 22918 kilojoules per mole. Okay, so this is the same way we were doing it. The bonds broken minus bonds formed, the heats that we have actually calculated. Uh, okay, so I'm gonna go through that. So from Lewis's structure to Whisper, this is the point where I wanted to bring you guys as soon as possible. So now we are done with the Lewis structure. This is where we are going to talk about the shapes of the molecule. Okay, shape of the molecule is very important because we are interested in the function of the molecule shape. Okay, not Lewis is not the three-dimensional shape. It's not the molecular geometry. Lewis structure is just a two-dimensional structure, which is not the true picture that how the bonds are going to orient themselves into the space. So Lewis is coupled with VSEPR, which is valence shell electron pair repulsion theory, that they go together. Okay, they go together to discuss the 3D shape of the molecule. What is the geometry of the molecule? What is the shape of the molecule? So when we talk about that, what we have done so far, if you go with these molecules here, okay, if you pay attention to these molecules here, what we are looking for is the bonds. Okay, if we talk about CH3, let's say here, not CH3, CH4, then we already know that there's going to be 4 bonds. If we draw that structure, that somewhere the Lewis structure is going to look like this, like, right? So the Lewis structure is like this, but that's not the true shape of the molecule. Why it's not the true shape of the molecule is because of the VESPR theory that we were discussing here. So we are done with the Lewis structure. We now know what the Lewis structure of the CH4 is going to be, but this is not like a flat or like a flat or on just one plane structure. Why? Because there's a concept of valence shell electron pair repulsion theory. What does that mean? Means these are the valence electrons shared between the two atoms. Valence electrons shared between the two atoms here. Valence electrons here. Because carbon must share its four valence electrons, right? So that's why these these are called the shared pairs of electron. They are going to repel each other. Okay, they're gonna go far from each other as possible as they can because they are negative groups, right? So what scientists have found when this is the situation, they're gonna go into the space and they're gonna get their orientation in the space in this way. So it's rather than we just draw this structure like this, a plus, sorry, what kind of plus is this? Okay, rather than we look at the CH4 structure like this, where center is carbon and then four hydrogen. This is not like that. They say the structure is where three bonds are going downwards, okay, and one bond is going upward. So it's going to be a four-phase object. If we just try to connect that, I'm sorry, that will be confusing for you guys. I have to use a dotted line for that. And if I use dotted line, so if this is the carbon, okay, so let's say this is your carbon in the middle, and then these are four hydrogens. So that if you start looking at this, that's going to be one, two, right? And there's going to be a third side over there, right? So um, so for tetrahedral geometry, it is means that it's going to be a four-sided object. Okay, the four-sided object that we call the tetrahedral geometry. The methane is going to acquire that. Why? Because of the repulsion of these. So VSEPR is based on the fact that electron pairs are repulsive to each other, want to get as far away from each other as possible, and that's where they are relaxed when they go all of them go far from each other to the best possible distance. They're going to stay there in the space, and that's how they're going to acquire their three-dimensional conformation. It's not going to be a flat on just one plane structure. Okay, it's going to be a three-dimensional structure that we're talking about. So then if we jump from CH3, so what we are discussing here was CH3. So if we from CH3, we look CH4, sorry, to look into another molecule here, which is NH3, right? And then this is H2. Oh, we have this example of these three molecules here. So we are looking at that. We are trying to discuss what is the possible shape for each of them. And in order to figure that out, so what scientists have figured out that when it's a tetrahedral shape, the bond angle between all of these bonds is going to be 109.5 degrees. Okay, exactly. So, so so look at this, look at that, look at that, and look at that. All the angles between, and there's one angle here to here as well, right? So these are going to be 109.5. All angles are of the similar distance because see, these are all similar bonds, CH, 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 CH. They all have the equal tendency to push each other, and that's how they're all gonna go at a particular specific distance from each other, and that is 109.5 degrees of the angle that is resulted because of their distance from each other. Okay, so then we are talking about the ammonia. Ammonia, if we draw the Lewis structure, if we draw Lewis structure for ammonia, that's gonna look like something like that. So I'm just quickly going to um, uh, what I'm going to. So if I draw the structure of ammonia, if I try to draw the structure of ammonia, I'm going to draw it like nitrogen goes into the center and three hydrogen is going to go like this, right? So that's going to be the Lewis structure for ammonia. Okay, so then there is going to be a lone pair here. That is the Lewis structure. So now what groups of electrons I have in the valence shell? This is one group of electron, and I have to point that out by just marking. This is one electron group between the two atoms, which is a shared pair because the bond is being formed. This is the second pair. this is the third pair of electrons, and this is the fourth pair of electron. What is the difference between all of them? These three are one, two, three are shared pairs, while this lone pair is unshared pair on the nitrogen. But total groups are four electron. These are four electron groups. These are four valence electron groups. But so this is the difference from here. When we draw the structure for CH4 here, CH4, then all four groups are shared pairs, right? These are all hydrogen going to be here. So when we draw this structure, okay, and we draw this here hydrogen, then all groups are shared pairs of groups. This group and this group here, okay. So that's the difference. That's the difference that we are looking at from ethane to ammonia. And if I go to water, then next is the water. If I draw the Lewis structure for the water, which we all know how to draw, is then going to be O here, and then that's going to be like this, H. So the green ones are representing bonds, and these orange balloons that you see, they are representing the lone pairs. So there's one lone pair here, so you see this orange one as a lone pair density of the electron here, and these greens are the density of the bonds actually, not the lone pair. So you're gonna have this H here, then you will have two lone pairs here. Okay, this is the Lewis structure for water. So that's going to be the H here. Okay. So now what do you see? You see, again, you see that there is going to be four electron groups. There are actually four electron groups. Okay. They're not, there, there are four electron groups in totality. I'm talking about the total electron groups. So this is your first one. Okay. This is your second one. This is your third one. This is your fourth one. Four electron groups around the central atom, out of which two of them are shared and two of them are lone pair or unshared pairs. So if let's say if we will move from ammonia, if you move from methane and we go all the way to water, then there were four, so it has four total electron groups are four here. Total electron groups are four here. Total electron groups are four here. What does that mean by electron group? The electron groups around the central atom. Okay, this is one electron group, this is another electron group, third electron group, fourth electron. This also has. So what is the difference from here to here? The difference is that out of four electron groups, one is a lone pair. Out of four electron groups, two are lone pair. That makes the difference in the shape. Okay. How come this is tetrahedral? So how come this shape is not tetrahedral? Because you do not have a physical bond here. Okay. Like a bond thing here. It's just a lone pair of electron. It means it's going to be, that was tetrahedral, but that is going to be trigonal pyramidal structure. Okay. Why? Why these three bonds are going down? Because this lone pair here is more powerful. You already know that the electrons in the bonds are stable than the electrons in the lone pair. Why? Because lone pairs are not bonded. They are relaxed. Comparatively, the lone pair is relaxed than just lone electron. But compared to shared pair of electron, which is actually a bond, lone pair is not that stable. It's pretty unstable compared to a shared group of electron that we show as a line here. Okay, so that's why it is more unstable. It's going to give more push to these three bonds, and that's why you see these three bonds are going downwards. Okay, and that object is going to look like a pyramid. So that's called as trigonal pyramidal geometry. And this one you see, two lone pair means two, it's going to be a stronger push. One was giving a good push to these three bonds here. Then when you have two lone pairs, it's going to be more push. So the bond angle you see is reducing from this example to the example of water. Because you see, this is a lone pair, this is a lone pair here, this is going to be shared pair, this is going to be shared pair. This is just one lone pair here. There is no lone pair here. Okay, these are all like this, are the same distance from each other. So what we are talking about here, that all bonds are going to be 107.3 degrees here in the example of ammonia, which is trigonal pyramidal geometry. When we look at this geometry here, that is the shape of the molecule. That's all we have, because this is just a lone pair and lone pair. So that's called band. Okay, band geometry, band. This is band, this is trigonal, pyramidal. The table is already available, so do not get confused about that. And that is going to be tetrahedral, okay? Tetrahedral. So that's tetrahedral. So, um, so just focus on that. What I was trying to explain here is important. And when we are looking at it this way, we need to understand what we are trying to. I'm really sorry about that. Okay, what we are trying to focus on. So let's angle that y angle is reducing from 9.5 degree to this geometry to that geometry, or the molecular shape of the molecule, right? That's the difference. How we know that the lone pair is there. So the difference in geometry is also based on when you do not have any lone pair compared to you have one lone pair compared to you have two lone pairs. So whisper in practice, okay, we usually call it whisper, but it's whisper in practice from a valid, so it needs to be a valid Lewis structure first. So if a compound molecular formula is given to you, the first thing is to draw a valid Lewis structure. You already know by now how to draw a valid Lewis structure. Then add up the number of group of electrons. As I was counting around that how many total valence electron groups, they, irrespective of shared pair of electron or a lone pair of electron, I'm just going to look for total number of valence electrons. Okay, so when it comes to the total number of valence electron, total groups of electron, then it is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So all of them have 4, 4, 4 electron groups. What is the difference is is when it comes to the lone pair versus the shared pairs of electron. So it keep that in your mind. We are looking at the central atom. Okay, we are always looking at the central atom and what is around the central atom in terms of the electron groups. This group, this total group, and this total group. Okay, so when we are looking at that, it's just a group. We are not going to this we're not going to have any different when we are counting a group. We're not going to look at the single, double, or triple bond. Okay, just all count as one group of electron. What does that mean? If you have this thing here, if you have triple bonded, let's say oxygen here, I'm sorry, space is always a critical issue here. So when you have this, sorry, when you have this C here and you have this triple bonded C here, which this H, and let's say H, this is a good molecule, it's a good representation. And you look at this H here, another H is attached here because carbon is going to make four bonds anyways. Okay, H here and H here. Then we are not looking at this atom. Right now we are looking at this atom. I'm sorry, this is absolutely incorrect. Why? Because carbon cannot make these many bonds here. Okay, so just one hydrogen will be attached to it here, like the one hydrogen is just four bond. Carbon goes for four bond. So we cannot make so many bonds. So one, two, three, four, one, two. So if I talk about this center here, and if I say how many electron groups, simply I'm saying electron groups. I'm not saying lone pair of electron, a lone pair electron group, or a shared pair electron group. I'm not talking about that. I'm just saying total number of electron groups around this atom. So it's going to be one and it's going to be two. Why? Because it doesn't matter. Single, double, and triple bonds all count as one group of electrons. Keep that in your mind. That's why it is in red. It's the most important thing. So then lone pairs and single electrons, as we have looked at it earlier in the case of free radicals, on the atom count as one group of electrons. So if it's a lone pair, if it's a single electron, if it's just single bond, double bond, triple bond, everything is going to be counted um, as one electron group. Okay, single bond is one electron group. Even if it is a triple bond, it's going to be one electron group around the central atom. Based on this number, you can actually determine the overall, which is called, so that we're going to talk about two types of geometries. One is called electron geometry. The second one is going to be the molecular geometry. Molecular geometry is actually the shape of the molecule. Electron geometry is not the shape of the molecule. Keep that in your mind. Electron geometry is including the lone pairs in it. Okay, not only the shared pairs of electron. That's why we're going to keep that difference here, and we'll do some examples and you will understand. Okay, electron and the molecular geometries. How do we do? There are only 5 electron geometries possible, so you can just quickly memorize it. The total number of electron groups will determine the overall electron geometry. The total number, that's why we were interested in the total number of electron groups. So if you remember what we had this here, right? This molecule, which is CH4. Here, here, I have another one here, let's say hydrogen. Okay. So how many total number of electron groups it has? 4. Now I'm going to look at the ammonia, right? So if I have ammonia here, not C, N, and then H, right? And then another H here, and then lone pair here. Again, it has 4 electron groups. Total number of electron groups is 4, right? Then if we have water here, then O, and if we look at the water, H, and then this is another H, and then you have lone pairs of electrons here. So again, 4 electron groups. It means they all have same electron geometry, similar electron geometry. 4, 4, 4, that brings us to the tetrahedral. But that's what we are talking about, the electron geometry. That's not about the shape. Shape is due to the lines here, not due to the lone pairs that you see here. Okay, lone pairs have nothing to do with the shape of the molecule. So if we look at this methane molecule, then this is 4. So you have 4 shared pairs, and you have 0 lone pair there. So 0 lone pair, right? So that is pretty reasonable. Or I can just make a slash here, okay? So then here you have 4 shared pairs, and how many lone pairs? 1 lone pair. Here you have 4 total shared pair. Oh no, I'm wrong. Okay, again going back to, it's not about the shared pairs. This time is where I can probably be a little lost, but let me go over it again. Okay, so they all have 4 electron groups. Okay, electron groups, 4 electron groups. We're talking about electron groups, right? See, when it comes to the electron geometry, total number of electron group. And so that's electron group. And this is again 4 electron group around the central atoms. Out of this 4, you have 4 shared pairs and 0 lone pair. Out of this, you have 3 shared pairs and you have 1 lone pair. Out of this, you have what? You have 2 shared pairs of electron and you have 2 lone pairs. This, what I'm trying to categorize it with the lone pairs. When I start looking at the lone pairs, then I'm talking about the molecular geometry. Number of lone pairs determine what the molecule is going to look like. Okay, it's simple. So when we talk about this, when you're talking about this, then it means that we need to go over with what we have for the molecules, decide for the electron geometry and the molecular geometry. Okay, So that's the difference. That's the main difference between the electron geometry and the molecular. Electron geometry, it considers total number of electron groups. It's not going to differentiate between the lone pairs of electron on the central atom versus the shared pair of electrons on the central atom. So no discrimination in that. Okay, but when it comes to giving the molecular geometry, see electron geometry to molecular geometry, then molecular geometry is when you start looking at the number of lone pairs. And that's how, even though many molecules can share the same electron geometry, they're going to have different shapes based on different number of lone pairs on the central atom. So these are the possible electron geometries with the 2 electron group, 3 electron group, 4 electron groups, 5 electron groups, 6 electron groups on the central atom. Okay, linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And these are the representative shapes of the molecule. That's how, if it's trigonal bipyramidal, the electron geometry, the shape of the electron cloud is going to look like this. So from here, we have to move on to the molecular geometry. Okay, so so now look at what are we looking for? When we are looking for the electron geometry and the molecular geometry, our focus should be on the central atom. Okay, always central atom. There may be molecules where you have 2 centers, like carbon to carbon, or 3 center to oxygen, like this, right? So you might have 3 centers here. Then you have to look at that what you have on the each center. Okay, so if it is going to go like this, or it's going to go be a double bonded here and going to get out of that, then you're going to say, this is your first center, this is your second center. Okay, and oxygen is actually attached to the second center. Then you have to do this exercise for each center one by one. Okay, so I will do that for you guys, and you will see what I'm trying to say about the multi-center molecules. Right now, what we have discussed is just one center molecule. So if we are looking at so if we are looking at carbon dioxide, let's say, okay, so the Lewis structure for carbon dioxide is I'm going to use this, okay? So the Lewis structure for carbon dioxide is C double bonded O here, okay? And then this is double bonded O here. Our concern is, so definitely there's going to be lone pairs here on the oxygen, but that has nothing to do with the shape. Our focus is always on the central atom, okay? So what do we have now? How many electron groups we have? Yes, so how many electron groups we have? We have actually 2 electron groups only. So this is considered, this double bond is considered as 1 electron group, and this is considered as second electron group on the central atom. Okay, so 2 electron groups, 0 lone pair. There is no lone pair on the central atom if you see that. Okay, so we are here on the chart, we are here on the table. Okay, we are here on the table. I don't know, this is pretty not that. Um, there's nothing in between, which is um, okay. So I'm going to keep using this one. Okay. So now what we see is the electron geometry is going to be linear, and molecular geometry is also going to be linear. Why? Because when there is no lone pairs on the central atom, then electron geometry is actually the molecular geometry as well. You see 2 solid things here, right? In the 2 bonds here. So trigonal planar. So if we talk about another molecule, um, which is NO3 nitrate ion. Okay, if I talk about nitrate ion, so the Lewis structure for the nitrate ion is going to look like this: O, O, and O, and this is going to be. Am I going to have a lone pair on the central atom? So how many? Five. Five. So if I calculate the valence electron, it's going to be five plus it's going to be six times three is 18. And then it's going to take this one more, so plus one. So that's going to be 24. Okay, 24 valence electrons. So it means one, two, three, four, five, six electrons are there. Then six times eight, six times three is 18. 18 plus six, 24, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There's 24 electrons that were supposed to satisfy here. Okay, okay, so good. So that's going to be the structure, and I'm going to write the minus charge here. And then I know that oxygen is greedy to make the double bond, so this is going to be shared as a double bond because nitrogen needs its octet, right? So nitrogen's octet is done by using a lone pair from one of the oxygens. And then there is going to be definitely resonance in this structure. One time the bond is going to be here, the second time the bond is going to be here, the third time bond is going to be here because all oxygen have the same tendency to make double bonds with the nitrogen in the center. Now, once we draw the Lewis structure, now, what are we going to do? We're going to look at the central atom, and then we're going to look at what do we have on the center, how many electron groups we have. So if we look at the electron groups, then we're going to say, okay, this is one electron group on the central atom. This is another group, and this is another group. Three electron groups, no lone pair on the central atom. So we are here. And what is going to be the electron geometry? Trigonal planar. As I have said, when there is no lone pair, then electron geometry becomes the molecular geometry. They both become similar to each other, right? So when we talk about the and if we talk about the bent trigonal, so if you look at this trigonal planar thing here, because electron geometry, three electron groups total, then it remains as trigonal planar, and trigonal planar as you look at three electron groups total. But if one out of three is a lone pair, then the shape is going to be bent. That's going to make the difference. You know that the lone pair is going to make the difference. If two lone pairs are there out of three groups, then it's going to be a linear structure. If so zero, there is no, none, then one, then it's going to be the bent geometry. If two, is going to be the linear geometry. So we'll keep working on different molecules, and then you will understand what I'm trying to say. But that's the general idea about it. Okay, so there can be many molecules having four electron groups, and we have already discussed three of those molecules. We have discussed methane, we have discussed ammonia, and we have also discussed um, water, right? They all had four electron groups, but there was a difference, right? When there were all four electron groups as shared pair, there is no zero lone pair, then the electron geometry is tetrahedral, and you already know when it's 0, 0, then electron geometry is actually the molecular geometry as well. But when we have four of the total electron groups and we had one lone pair in case of ammonia, then electron geometry remains the same because you have four electron groups in total, but one lone pair out of four is gonna make it trigonal pyramidal. Then what we are doing here is that when you have four electron groups, as with the example of water, and two of them are lone pairs, then the electron geometry remains the same, but the molecular geometry is bent. That's what we have looked at in water. Water has a molecular geometry that is bent. Okay, so you understand this. This is very important that you understand it. Okay, because it has some importance. Okay, the rational, one of the learning objective, major learning outcome of this course is to understand this, that how you have different geometries, shapes of the molecule. So because we have a total 5 possible electron geometries, 1, 2, 3, 4, and 5. So we can keep going on with the number of electron groups, out of which how many of them are lone pairs. You're gonna have different shapes. Okay, the most important part that I would like to say that focus on this table, this tells you exactly where the atoms are going to be and where the lone pairs are going to be. Okay, it is very important to focus on this chart because this chart is going to help you determine the polarity of the molecule later on. So if you have two electron groups and none of them are lone pairs, then you're going to have a molecular shape like this, right? The molecular shape is going to be like this with no lone pair. It's going to be linear. Okay, so when it's linear, then your atom X is here, then you're going to have Y here and Y here. So that's the shape linear of the molecule. That's the shape of the linear molecule. There are different possibilities where molecule can be linear. That's not the only possibility with 2 and 0. Okay, that's not the only possibility. You see here, where you have 5 total electron groups, out of which 3 are lone pairs. There also you will have a linear geometry of the molecule. That's why I'm telling you to focus on this chart really well. Why? Because all the lone pairs here are going onto the equatorial position. When they are on the equatorial position on the same plane, they're going to cancel out each other's effect, and they're not, because they are all going to push the same push, put the same push onto these two bonds. Okay, so the push from this side to the push from this side is balanced on the molecule. That's why these bonds are going to go in this straight line like this. Okay, and that's because when we are talking about the shape, we are not considering the lone pairs. Then the shape of the molecule is going to be like this, linear, exactly how it was linear here. Okay, that's important. That's where you're supposed to focus. Okay, so let's talk about this. Another linear conformation, another linear shape of the molecule. But what you have 6 electron groups here, out of which 4 are lone pairs. Again, you see these lone pairs are going onto the equatorial position, and they are going to cancel out. Cancel out means they are going to put exactly the same push on this side compared to the push on these two bonds on the other side. Okay, repulsion. This is what I'm talking about, the valence shell electron repulsion theory. Okay, so if you just know what I'm trying to talk about, then we do not show in shape the electron. The lone pairs of electron has nothing to do in it. The shape is determined by the solid line, which is shared pairs of electron. That's why it's linear. Now, I think you now understand what I'm trying. It's very important that you understand, go through it, read about it, and try to understand. And I'm also going to share the simulation for the molecules into their three-dimensional structure or their geometries. You can go through that as well, so it will be a better understanding for you what I'm talking to talk about. So at this point, I would like to finish this lecture here. So we'll continue with another video. I'm going to continue this lecture, this chapter number 7 with another video. But right now, I'm going to stop this session here. And let me know if you guys have any questions on um,